Hello, and thanks for reviewing the following presentation given during the 2020 Data Science Symposium webinar series. The Data Science Symposium is one of several services provided by the University of Cincinnati's Center for Business Analytics, a part of the Lindner College of Business. Through leadership forums, student projects, public education events, including the Data Science Symposium and the Analytics Summit this spring, as well as professional development courses, the Center provides businesses and organizations with game-changing capabilities to drive analytics for competitive advantage, regardless of size or type of organization you represent. For more information about the Center, including how to join our 25 member organizations and the benefits they enjoy, please contact either myself or Dr. Michael Fry here at UC. Now, enjoy the following presentation.
Next up is Matt Brems. Hey Matt, would you mind turning on your video?
Yeah. Hey,
Matt.
How are you?
Hey, nice to see you.
Yeah,
so,
you too.
Matt is currently managing partner and principal data scientist at Betavector. His full-time professional data work spans finance, education, consumer packaged goods, and politics, and he just earned General Assembly's 2019 Distinguished Faculty Member of the Year Award. So Matt, maybe you can tell us a little bit about your background and what we're going to hear from you today in your talk.
Yeah, so thank you so much for the introduction. Like you mentioned, my full-time data experience spans a lot of different industries. And one of the things that I noticed pretty continually throughout my work is that missing data is incredibly important. Missing data shows up in, or rather, I guess doesn't show up in just about every context, and whether you're in education or finance or consumer packaged goods. And it's really important to pay attention to that. So that's one of the things that I'm particularly passionate about. But back in I guess a few years ago, I earned a degree in statistics, and what I found pretty quickly was that the treatment of missing data was very, very theoretical. It was something where most of the textbooks out there are designed for people who have maybe a master's or a PhD in statistics or in math. But there are so many practitioners out there who need a more tangible way to think about and to understand missing data that doesn't involve buying a 300-page textbook and diving into all of that. So that this is sort of the problem that I've been really passionate about helping people to solve. And so that's part of why I'm here today.
All right, that sounds great, Matt. So I'm going to turn things over to you. And so if you don't mind sharing your screen, just a reminder for all the attendees, please do use the Q&A feature. And just like we did with Marshall, if you type in questions there for Matt, we'll aggregate these and then we'll ask Matt verbally as many as we can after his presentation concludes. So with that, Matt, take it away.
All right, thank you very much. Are you able to see my screen?
Yes, we can. Thanks.
Okay, perfect. Thank you. And welcome everybody. I'm very excited to be chatting with you today. My name is Matt Brems. I use he, him pronouns. And today I'm doing a session on good, fast, cheap, how to do data science with missing data. So the first thing that I want to pull up is that generally I have given this talk at conferences over the span of like a 3.5-hour training session. I've done a lot of abbreviated versions of it, but 20 or 25 minutes is pretty challenging. Like I mentioned, a lot of graduate programs will do an academic treatment of missing data where as a graduate student, you may take a full 1-semester course on missing data. So we're going to do a very abridged version, but let's say that you want to know more. Feel free to head to my GitHub profile. I have the entirety of the 3.5-hour talk that I generally give. And I also dropped this link into the Zoom chat. So you should be able to just click that and head over there. It's not required. You may not be working with multiple screens and you may just want to bookmark that for later, but wanted to at least share those resources with you at the top of our time together today. So with that said, I want to talk very quickly about the idea of good, fast, cheap. And I think that a lot of us have probably already talked about or are familiar with the notion of good, fast, cheap. And if you're not, it's an idea in project management where when you're working with a manager or with a client or on any sort of project, the goal is to get things done in a way that is good, in a way that is fast, and a way that is cheap. But As we all know, having done projects, it is impossible for us to tackle something that is good and fast and cheap. And if you look at the intersection of these three areas in the Venn diagram, your client or your boss or whomever, they're probably dreaming if they want all of these things. We can usually only pick two of them. We can pick something that's good and fast, but it's not going to be cheap. It will end up being more expensive. We can pick something that is good and cheap, but it won't be done quickly and it will take time to deliver. Or in many cases, somebody will say, I need this tomorrow and I'm not willing to pay very much money for it or put forth the resources. So it's both fast and cheap, but generally things end up not being the best quality. I like to use this to apply to missing data. So when we think about missing data, I want to break the approaches down into three main sections. There are analyses that you can do that are fast and cheap. So you can just, for example, drop every row that contains missing data, or you can do something called single imputation, and we'll mention what that is. But that tends to be fast and cheap, and what that means is that it tends to not be good. A good analysis that is also a cheap analysis would be to use something called proper imputation or the pattern submodel method, and we'll talk about both of these. The problem is that these are not generally fast methods to use, and they take some time to use properly. And then the other approach that you might consider is if your analysis should be done well and can be done quickly, it ends up being pretty expensive to do this. You just have to gather your data in a complete manner up front. So when you're doing surveys, you may need to follow up with people many times to ensure that, for example, you don't have any missing data. But obviously that can be expensive and it's tough to articulate that to a client or to a manager and get them to buy onto this. The reason that I like setting the stage like this is that everything here is a trade-off. The decisions that you make, I'm not here to say that there's one decision that you always should make. There are certain ones that are methodologically better and more appropriate for us and for you and for your team of data scientists. But that doesn't mean that necessarily you always need to do one thing, but we should at the very least be aware of the trade-offs that exist. So the agenda for our talk, I'm going to talk through 6 different strategies for doing data science with missing data, and we'll round out with some practical considerations and warnings that I encourage you to be aware of as you think about these trade-offs. So at the very start, the first thing is to avoid missing data before it even happens. It is generally, in my experience, cheaper in the long run, but more expensive upfront, which makes it a tougher sell, to avoid missing data than to make guesses or estimations about how to handle missing data. So for example, I like to discuss, I am an avid fan of Buffalo Wild Wings and Chipotle, and both of them offer, customer service surveys that I can complete. Chipotle, if you order through the Chipotle app, asks at most 2 questions. It's done entirely on your phone. It's very easy. They don't promise anything for you. I don't even think they offer a chance to enter and win something, but I always find myself filling out the Chipotle survey. Buffalo Wild Wings, on the other hand, prints out a receipt. There's a long code on the bottom of the receipt. You have to go to the computer, type in the link, type in the 16-digit code they give you, fill out 30 questions, including some open-ended questions, and you're given free fries as a result. I have never finished that survey because of all of those steps that come into play. So this gets to the idea of avoiding missing data. This is not as exciting or as interesting as maybe talking about advanced modeling techniques, but are there specific decisions you can make that, for example, may decrease the burden on your respondent, or that may change your method of data collection so that things are done electronically and there are fewer hurdles in the way for people to give you their data, should they choose to give you that data. So I've got a couple of bullets on here for different ways of avoiding missing data. It probably does not surprise anybody that minimizing the length of your questionnaire, for example, people will be likelier to respond to 2 questions as opposed to 50 questions. So this is a very, very rapid discussion of how to avoid missing data before it even happens. However, in many cases, and depending on where you are in the data analytics or the data science workflow, you may get data that already has some missing values in it. So now the question is, strategy 2, can we ignore missing data? If you choose to ignore missing data, which generally just means you continue doing your analysis, kind of pretending like they aren't there, perhaps you drop all of your rows with missing data, many software packages will default to doing that. You assume implicitly that observations for which you have observed your data are similar to observations for which you're missing data. That is a pretty dangerous assumption to make. For example, thinking about political polling, it's a very common topic these days. If a pollster chooses to make telephone calls to landlines, which based on legal reasons, many organizations do call landlines because it's cheaper to do so, they may only call during certain hours of the day. Let's say that they call between noon and 5 p.m. in the day. Well, if they call between noon and 5 p.m., obviously these are very weird times that we're living through, so this may not be as significant a bias, but historically, many people would traditionally be working during that noon to 5 time, and would that skew the results of the questionnaire? The answer is probably yes, and that's something that I've observed personally when working with that. So that assumption is not necessarily a benign assumption that we want to make. So as you think about this, think very, very critically and be very skeptical about making that assumption, should you choose to make it. One, people often ask for like, what is the threshold or what is the right amount of missing data where you can safely ignore it? The short answer is that there isn't one. The very general guideline that is not a one-size-fits-all solution, but the guideline that through my experiences, what I've been told and taught by others, is that if you are missing less than 5% of all observations in your data, that you may be okay ignoring missing data. Now, that's not always the case. If you have a Y variable, that variable that you're trying to predict or forecast, if all of your missing data comes from that column, you may not be comfortable ignoring that missing data. So you want to proceed with caution. You don't want to take any of this as this rule, like this condition of less than 5% has been checked, therefore I'm good to go. But instead think more intentionally about, is this okay? So those are strategies 1 and 2, avoid missing data and ignore missing data. The remaining 4 strategies that I'm going to go through talk about accounting for missing data, but I find it helpful to shift our mindset before we get into these 4 examples. There is a naive belief by many, myself included when I started learning about this, that we could just plug in those gaps in our data. There was a way to just impute or fill in those missing values. But effectively what we're doing is we have to do this in a certain way, or we are making up data, which in my experience and in my opinion is a very, very unethical thing to do. Making up data is not an ethical thing to do as a data scientist. So what I want to articulate here is that in most cases, we're not fixing our missing data, or we're not fixing this problem. This isn't one step in the data analytics workflow, but instead we're learning about how to cope with missing data. So as you may have noticed, the title of my session is Good, Fast, Cheap: How to Do Data Science with Missing Data. And it seems subtle, but I think it's an important mind shift for us to have, to think about. It's not, oh, I just fill in these values, check that box and move on, but instead, how do we do data science in the presence of missing data? So we've talked through those first 2 strategies. Now let's get into deductive imputation and move through the rest of these. Deductive imputation is just about using logical rules to fill in missing values. So suppose that you administer a questionnaire, and one of the questions on this questionnaire says, have you been in a car accident in the last 12 months? And the respondent says no, or replies no to that. The next question in the survey might say, were you the at-fault driver in a car accident in the last 12 months? Perhaps the respondent leaves that blank for one of many reasons. Well, in this case, we don't need to worry about statistical estimation or prediction. We know logically that if that person has not been in a car accident, then they were not the at-fault driver in a car accident over that same time frame. So even though that data is missing, we can just fill in that missing value based purely on logic. And the only assumption we're making is that the person was truthful in the prior answer. Now, some of the considerations here. If you are working with the same data set over and over and over again, or the same type of data, like the same questionnaire, it might be administered to different people, but it's the same questions, you can automate these checks. However, if you're working with different data sources every day, that can be time consuming because it requires specific coding on your part to understand what are the relationships between the variables and where can you impute values and how does all of that work. But luckily, it requires no inference and it can be used regardless of missingness type. Down here, I write missingness type. There are, in the interest of time, we can't go through the 3 different types of missingness, but there are things called missing completely at random, missing not at random, and missing at random. Please do not shoot the messenger. I'm not the person who came up with these terms. But these 3 different types of randomness, missing completely at random, missing at random, and not missing at random, if you can detect whether or not these things exist in your data, that may influence some of the decisions you make. And in my GitHub repository, I have more comments on what those are and how to perhaps detect for those. So deductive imputation uses logical rules to fill in missing values. Moving on to single imputation. So commonly we might think of mean, median, or mode imputation. So for example, I've defined it up here. There's any NA or any missing value in a given column. Just replace that missing value with the mean or the median or the mode of your observed data. It's something that's quick, it's easy to implement, and it seems reasonable, but it can significantly distort your histogram and it will underestimate your variance. I want to show on the next slide what I mean by that. I've simulated some data here where up top, this histogram is the real histogram of age data that I'm working with. And let's say that I take 30% of that data and set it missing. And I set it missing completely at random. So there's no rhyme or reason why certain observations are missing. If I were to impute the mean for that, this histogram now gets very, very distorted. This orange bar here represents all of those imputed values that were missing, but we've now filled in the mean. So it can distort what our histogram looks like. If we continue to think about the mean, if you'll indulge me for a minute, we're also underestimating our variance. So what we have on here, I'm not going to go through each of the individual steps and welcome you to do that on your own if you like. But this formula on the screen is the sample standard deviation. So you may recognize that, you may want to check that out. But all we're looking at is the sample standard deviation. And this is the formula where if I have a sample size of n, and I have observed the first k observations, and I'm missing the bottom k plus 1 through n observations, what does this formula look like? Well, if I take the sample standard deviation for those first k observations, then I fill in the mean for all of those missing values, what ends up happening? I encourage you to maybe take a look at this on your own and how this works out. But for all of those observations that were missing, but we now filled in the mean, what you may notice from the standard deviation formula is we're taking the mean minus the mean squared, and we're just adding that up. Well, the mean minus the mean is just 0. Squaring 0 gives us 0. Adding up a bunch of zeros continues to give us 0. So what ends up happening is that we end up dividing by a larger sample size, in this case, sample size of n, because we filled in missing values. But the numerator, or this summation part, that doesn't get any larger. Why do we care about this? Well, if you care about doing any sort of confidence interval or any sort of hypothesis test, that confidence interval, suppose you say you want 95% confidence, just by imputing the mean, that will artificially get smaller. So it looks like you're more precise. It looks like you're still 95% confident, but over a smaller range. So that may make you overconfident in your results. The same thing would happen with a significance test or a p-value. Your p-value will artificially get smaller. So whereas if you had the real data, your p-value may be 0.07, after imputing the mean, that p-value may change to 0.04. Well, by doing mean imputation, you may now get a p-value that looks significant, and perhaps if you rely on p-values to make decisions, you may make a different decision than you otherwise would have just because you chose to fill in the mean. So underestimating variance can be a really problematic thing, even though filling in the mean or the median or the mode might seem like a logically reasonable thing to do. Here we can see if I were to impute the mode in this case, notice that this pretty significantly skews my histogram, or distorts that histogram as well. That orange bar has just moved significantly over to the left. Now you might be saying, well, what if I don't want to fit one value? I don't want to do the mean or the median or the mode, but maybe I fit a regression model. So again, there's a lot of words on this slide, but we just want to maybe fit a model based on where I've observed all of my data. And then the way I'm going to fill in, or I'm going to impute those missing values, is to just generate predictions from that model fit on the data that I've observed. This seems reasonable, but we're going to run into similar issues. If I show you this histogram here, this histogram, the real histogram up top, is of age. And down below, when I show you what's observed and imputed, notice how the orange values, those imputed values, still tend to clump toward the middle. We can see this even more vividly if I show you a scatter plot of what this would look like. On the left-hand side, we see something called deterministic imputation. So these thick black dots here, those are what are imputed. Those are the values that we have filled in from a regression line. But notice that those black dots don't seem to match the scatter of all of the smaller gray dots, or the gray observations that we have there. Instead, we may want to try something called random imputation, where in this case, we add some random error to our missing our imputations. And those black dots seem to better match, or better align with, that broader scope of things that we are observing. So the approach for regression is we're actually going to do something called proper imputation. I have up top, if you or your teams are users of R or Python, you can use the mice package in R or the multiple imputer package in Python to try and do some of this for you. But the strategy behind this is to take our data, make a bunch of different copies of that same data set, still develop a regression model, but add some random error to each of our predictions, so that when there's a value, for example, this value was missing and is imputed as 7. Over here, that value was imputed as a 3. There's random error every time that you impute. You do that for however many copies of your data set you have. I've written 10 over here, which is a good number to get. The more, the better. In this visual, we just have 3 copies of that data set. What you would then do is do your final model or your final analysis on each of those data sets. So you would have the 3 data sets, or the 3 sets of results down here. It looks like in this visual here, somebody has fit a couple of linear regression models, and they've got the parameter estimates and the standard errors for each of those. And then there are a set of rules called Rubens Rules to combine those together if you would like. If you want to use proper imputation for generating predictions, it's very similar to, for example, if you know of random forests, you're going to average your predictions together or select the plurality class, whether you're doing a regression or a classification problem. So you build out those 10 different models. You've got 10 models. You pass your predictions through each of those 10 models, and then you aggregate those predictions together in the same way that you would like aggregating results from multiple decision trees in a random forest. If your goal is to do inference, so you want to understand how does the value of beta 1 change from one model to the next, and how do you combine those together, the rules get a bit more complicated. There's something called Rubens Rules, and in that repository that I shared with you, there's a couple of links in there if you want to take a look for resources on how to implement that and what specifically Rubens Rules are. That brings me to what I call the pattern submodel approach, and this is my favorite approach. If you were generating predictions, this is super intuitive and generally has performance that outperforms any sort of simple imputation model. You take your data sets here, and you break it into subsets based on the missingness pattern. When I say the missingness pattern, I mean how are these NAs organized? So what you would do is something like this. Notice in our data set, there are 2 rows where we have observed Y and x1 and x2. What you do is you just take that subset of your data and fit a model on that. So I wrote this out as if it were a linear regression model, where you fit a model to just those two observations. You then move on to the second subset of data. And in the second subset, you only have y and x1. You no longer have x2. So on those observations, you fit a model to just y and x1. Down below, you do the same for y and x2. And in the very bottom here, at the bottom of the screen, if you do have a case where you've only observed y values and you don't have any inputs, you just take the average of those y values or the median of those y values and use that as your prediction. All the pattern submodel approach does, takes your full data set and breaks it up into subsets based on what's observed and what's missing together, and you fit a model on all of that. So how do we pull these pieces together? I know we are running toward the end of our time together. How do we pull these pieces together in one workflow? So the strategy that I take is I start by saying, how much missing data do I have during my exploratory data analysis? And is it worth my time and perhaps my money to try and address this or account for this missing data? Then I move into saying, can I do deductive imputation? Can I use logical rules to fill in these missing values? Then I sort of bifurcate along a path. If my goal is to do predictions, if I just want to get the model with the best mean squared error, the best accuracy, at that point I use the pattern submodel method, where we break our data into subsets and generate one model for each of those subsets. If I want to do inference, if I want to understand the relationship between x1 and y, for example, then I try and use the best imputation method available. So I would try and use proper imputation there using, again, either the mice or the multiple imputer package. So those are the 6 strategies for doing data science with missing data. I have 3 quick practical considerations that I encourage you to keep top of mind because this will hopefully save you some heartache. First, if your goal is just to get a full, complete data set that you can save and pass on to someone else, be really careful. Because once you've constructed that data set, nobody will know the difference between the data that is observed and the data is imputed. And so if you have your full set of data and you send that to an intern, a manager, a client, whomever, they may not treat that data that's been imputed as if it was imputed. They may believe that that was all generated correctly. So that's something where you want to be very aware of that. So that's warning 1. Warning 2. Improper imputation is making up data, and I believe this to be an unethical thing to do. Just filling in the mean age, for example, you are putting in data or making that data up. Proper imputation, where you do multiple imputations and you build a bunch of different models, isn't making up data. And I'll be honest, this was something that was uncomfortable to me when I first learned it because I didn't believe the professor who said it. And it took a long time for me to get comfortable with this idea because it did feel like it was making up data. Proper imputation is not making up data. Proper imputation is allowing you to impute or fill in missing values, but you're filling in multiple values that reflect how certain you are in the variability in that data. So when you fit that regression line and you use random errors to explore different values for that, that is going to better estimate how much variability is actually in your data and what is your belief about each of those missing values that you put in. The last thing is that there are sklearn methods or scikit-learn methods in Python like single imputer and iterative imputer. Last I checked, iterative imputer is currently experimental. So if I have to say use R or Python, I do recommend that you use R. If you use Python, just proceed with caution. Don't take this as, as law and say, okay, I will use this and move forward with it. I would just encourage you to proceed with caution there. So this is where I've got just the rehashing of that set of Venn diagrams. What are the different trade-offs that you want to be aware of, and what are the trade-offs that may affect the work you do and the decisions you make? I've re-upped that link. If you want to take a look at that, again, I did put that into the chat. And then thank you all very much.